Right, this video is on chapter 11, part 3 on histograms. So we use histograms to represent group data with class intervals. So you've seen this phrase in your Sec 1, chapter 14, data handling, part 2 on group frequency tables. So a histogram consists of rectangles whose areas are proportional to the frequencies. Let's compare that histogram with a bar graph. So on the left-hand side, we have an example of a bar graph showing the number of cars rented out by a company for a period of 6 months. So in our horizontal axis, we have the first 6 months of the year. And in our vertical axis, it shows the number of cars rented out for each of these months. Now a bar graph, it has a set of vertical, which is shown over here, vertical bars or rectangles. Sometimes it could be horizontal. There is uniform spacing between each of the bars or rectangles. So as you can see, there are two tiny squares between each of the bars. So we call that uniform. It is constant. The height of each bar and rectangle is proportional to the frequency. So here in our first rectangle, we've got 22 cars in January. So if we actually try and measure this height, you'll find that whatever centimeter that is corresponds to our 22 cars. That same scale is being used for all the other rectangles. So that can actually be seen from all these constant little squares where each tiny square has a height of, representing a height of 2 cars. Next, the base of the rectangle, meaning the width, has no meaning. So the width over here, we see that they have used 3 small squares to represent the widths of each of these bars. But they could have used 4 squares, 5 squares. As long as it is presented neatly, it is fine. But the width itself doesn't have any meaning. So we compare that with a histogram. So on the diagram on the right, we have the histogram showing the number of pets, a cluster of flats in a estate heaps. So we have on the horizontal axis, the number of pets, the vertical axis, the frequency. Now the data is grouped into different class intervals. In this example, we've got 1, 2, 3, 4, 5, and 6 class intervals. There is no spacing between the different rectangles. So you can compare that with our bar graph. Bar graph has constant spacing. Histogram has no spacing at all. The areas of the rectangles are proportional to the frequencies, and the base of each rectangle represents the class width. So this is again class width is a term that was used in chapter 14, part 2 of the notes. Let's move on to the next page. Now let's try and construct a histogram of equal class intervals. So when we talk about equal class intervals, the class width will be the same. They have the same thickness for each of the bars or rectangles. So here, the skills that you need is actually the same from what was taught or introduced in chapter 14, part 2 of the notes. So here we have the time in minutes that 30 students spent on their homework on a particular day. So we need to do the tally and count the frequency. So let's start with the first one. Please take note that in this case, x is greater than or equal to 0. So x can be 0, but it cannot be equal to 20. So anything from 0 to less than 20, we're going to count it in the first row. So 0, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So you continue with this counting, make sure you do it accurately. This is what you should see. 9 in the next class interval, 8 in the next class interval, and finally 2 in the final one. So always make it a habit to just do a sum. So we see that there are 30 numbers over here. Check that you have 30 numbers so that it means you did not miss out any number or you did not double count. So here we have upper class limits. On the right hand side. And we have our lower class limit. Okay, so the bigger number will be the upper, the lower number will be the lower. So the class width is our upper class limit minus the lowest class limit. And this range over here, we call it the class interval. So in part B, it says that we have to construct a histogram with equal class intervals to illustrate the data above. So do your planning, and with a ruler and pencil, start drawing your vertical and horizontal axis. Our vertical axis will be our frequency. Horizontal axis will be representing our time in X minutes. Okay, so our class intervals, the first interval is from 0 to 20. And we have 4 such intervals. So make sure you have enough space. So if I choose this to be 20, from 0 to 20, 40, 60, and 80, I see that I have enough space. And the class width, they're all uniform, constants. So let's continue with the vertical axis. Now our vertical axis goes all the way from 2 to 11. So we have to ensure that we have enough space for that. So this is the scale I'm going to be using. 5 tiny squares will represent 2.5. So 10 tiny squares will represent 5 for the frequency. In the first 0 to 20 class interval, the frequency is 11. So let's plot that out. This will be my 11. Okay, so draw with a ruler. This is my first bar. The second bar is for frequency of 9 from range 20 to 40. So from range 20 to 40 to reach 9, this is what we have. The next interval is from 40 to 60, and we have a frequency of 8. Finally, from range 60 to 80, we only have 2. So that will be our 4 squares. And this is our histogram. Let's move on now to example number 2. Here we have the following data for the masses in kilograms of 30 newborn babies. So our vertical axis shows again our frequencies, and our horizontal axis shows the mass. So just a recap, this symbol over here shows that we have truncated the horizontal axis because the numbers before 2.8, they are not relevant. They're irrelevant. If we draw the entire horizontal axis, there will be a lot of wasted space. So we don't want that. We sort of crumple it up with this symbol. Now, let's start with the model class interval. So that talks about the mode. In this case, the one with the highest frequency refers to this particular interval. So we call the interval from 3.4 less than x less than or equal to 3.6. This is the interval with the highest frequency. Next, we have the class width. So the width of each rectangle is the class width. So we take the upper class limit minus the lower class limit. That would be 4.0 minus 3.8 to give us 0.2. You can use any of these rectangles to calculate the class width. In this case, they are all equal, so it doesn't matter. You will always get 0.2. And then the height of each rectangle shows the frequency of each class interval. The area of each rectangle is proportional to the frequency of each class. So in a case where the class width is constant, then the frequency will be proportional to the height, just like your bar graph. So here, for the interpretation for this diagram above, we can conclude that the masses of newborn babies, they lie between 2.8, that is the lowest, and the highest, 4.0 kg. Most of the babies, most of them weigh between 3.4 and 3.6 kg. That refers to the model class. So practice number 1, please try this by yourself. Okay, you have already acquired the necessary skills to fill in the blanks for the frequency. One clue is that there are total 120 adults. Then you also have to fill in one missing bar graph, one missing rectangle over here. Class width, take the maximum minus the minimum for any of the class intervals because these are all uniform. Okay, part C, simple question that you can do by yourself. Part D, I'll give you the answer, but make sure you figure out why it is 70. Model class interval, do it yourself, and try to come up with an explanation for why Jane could be wrong. This will be discussed in class. We move on now to practice number 2. So here we have the marks of 76 students in a mathematics test. So again, construct a histogram in a space to represent the marks. So I'll pause your video here, construct the histogram by yourself first. Okay, so do a check. Is this what you have? Because if this is what you have, you are almost correct. Take a look at the horizontal axis. We start from 0. The next number that we see is 30, followed by 40, 50, 60, 70, and 80. So the scale is not constant. Please include this symbol at the side. So it tells the reader that you are aware we are supposed to have more numbers over there, meaning our 10 and 20. But since they are not in use, we're just going to crumple that portion up. So now write down the class width of each class. Very clearly, the class width is equal to 10 marks. Doesn't matter which bar you used, it will always be 10. So write down the number of students who score more than or equal to 50 marks. More than or equal to 50 marks. So we are interested in these data, these values. Okay, you can also tell that from the graph. So adding 22, 15, and 12, we get 49. So the percentage is 49 over 76 times 100%. And we get 64 and 9 over 19%. There's no reason to round off. So now find the number of students who scored more than or equal to 40, but less than 60. More than or equal to 40, but less than 60. So now we are interested in this group, which again can be seen from your histogram. More than or equal to 40, but less than 60. So that'll be 15 plus 22. That is the number of students. And then for the fraction, (37 over 76). Now in part E, we have another histogram, the marks of the same 76 students in another subject, English test. So now find the percentage of students who score more than or equal to 50 marks. So more than or equal to 50 marks refers to this region. So just do a quick count. We've got 15 here, 13, and 10. So percentage will be the sum, 15, 13, 10, we get 38 over 76 times 100%. So you get 50%, just nice. Now in part 2, which subject did the students have a better performance? So in this case, what we can say is that comparing, because in part 1, right, we looked at the percentage of students who scored more than or equal to 50 marks. In English, it was very nice, 50%, but in mathematics, we had a higher percentage. So we can actually use that as one of the ways to compare. So a larger percentage of students scored more than 50 marks. Okay, so a larger percentage. Let us indicate how much is that. 64.5%. Scored more than 50 marks in mathematics. Then in English, which was 50% only. This is one of the evidence that we can state. Then we also can talk about the model class interval. The model class interval mark for mathematics is 50 to 60. Which is actually higher than the class interval. Mark for English, which is from 30 to 40. So most of the many students lie in this interval for mathematics, 50 to 60. Many students lie in this interval for English, which is 30 to 40. So based on these two evidence, number 1, number 2, we can conclude that students did better in mathematics. So now in part 3, calculate the estimated mean for the English test. So to calculate the estimated mean, you will need to find the mid value for each of the class interval. We also call that the class mark. So we simply take the average of 30 and 40 to find the center value. That would be 35. Next, we have 45, 55. Because the class widths are constant, then we are just going to be adding a constant value of 10 to the previous class mark. So right now I've written all the different class marks, and we're going to use these values, for example, 35 multiplied by 21, because what we are effectively saying is that 21 of these students, yes, they got a mark between 30 and 40, but because the data is presented in such a way that we do not know exactly what each student obtained. We do not have the raw data. So what we're going to say is that these 21 students, they scored approximately 35 marks. And that is why it is an approximation. We're going to continue to say that 17 students, they scored approximately 45 marks. Clearly, this is not exact, but that is why we are calling it an estimation of the mean, because we have lost data. So in part 3, the mean represented by x with a horizontal line on top, we take 21 times 35 plus 17 times 45, continue with 15 and 55, 13, 65, 10, and 75. So we add all of those up, we divide it by the total frequency, which is 76. We end up with 51, 11 over 19 marks. No need to round off. Now we come to the last page, where we talk about the different types of data and statistical diagrams. So along the way, your teacher may have mentioned these two words, discrete and continuous. So I will start with continuous first, because we kind of have an idea what continuous means. So there are data values that can take on any value in a certain range. So generally, we say that these values are to be measured. So examples will be, for example, time. Time can take a value, any value in a range. Distance is another example. You can keep on subdividing an interval in time. You can keep on subdividing an interval in length to get the precision that you want. Compare that with discrete. So discrete is like the opposite of continuous. There are values that can only take on certain individual values, and these are values to be counted. So it will become clearer to you when we do this activity. So we are supposed to match the following description to either discrete, meaning to be counted, or continuous, which is to be measured. So in the first one, it talks about the number of pages in a book. If I want you to determine the number of pages in a book, you are going to count. The numbers are going to be integers. You're going to have 1 page, 2 page, 3 pages, 4 pages, so on and so forth. You cannot have 3.15261 page. Okay, so in the first example, this is actually a discrete data. The next one, the length of a leaf. How do we obtain the data for a length of a leaf? We are going to have to measure it. And the length of the leaf will fall within a range. There is a minimum length that a leaf can have. There is a maximum length that a leaf can have. It can't be infinite. So this length can lie anywhere within this range. It can be a decimal. It can be an integer. So we call this a continuous data. It lies somewhere on the number line, anywhere on the number line. Doesn't have to be an integer. Next one, temperature of a patient. So although your thermometer shows you up to 1 decimal place, the reality is that it can even go to 2 decimal places, 3 decimal places, 4 decimal places. And we use a thermometer to measure the temperature. So that again is an example of continuous data. Now, size of the shoe, that's the fourth line. The size of a shoe, do not confuse this with length of the foot, because a human's length of the foot is going to be continuous. Not everybody has the same length. Not everybody's feet are measured in integers. However, the size of a shoe is given in fixed numbers. For example, 8, then you go on to 8.5, 9, 9.5. So these are discrete values. They are fixed values. You can't get a shoe size that is 8 and 11/97. You can't. So that would be a case of discrete data. Now, time taken to swim a lap, again, measurement. Number of cars in a household, that will be counted and that will be discrete. So I hope this gives you a better idea of what discrete and continuous are. Now we have the final activity over here. We are supposed to match whether these different statistical diagrams are relevant for or considered representations of discrete data or continuous data. So let's start with the first one. On the top left-hand corner, we see a dot diagram for the number of letters. So number of letters, we are able to count them. They will be in integers. So that will be an example of discrete data being represented in a dot diagram. On the second one, here we have a histogram for the mass of apples. Apples, they have varying masses, and the masses do not necessarily have to be integers. They do not necessarily have to be in intervals of 0.5 grams, for example. It can be anything. So that will be continuous data. You have to measure it. Next, you have bar graph for the number of goals scored. So again, a clue, number of goals scored, that will be discrete. The stem and leaf for, again, number of defective light bulbs, that will be discrete again. Pie chart. Pie chart for the number of times the student eats fast food, that will be discrete. Line chart for exchange rate. So money exchange. Money exchange, if you've been to a money changer, you see that there are many decimals usually displayed for the exchange. And they don't necessarily have to be in any fixed options. So that is an example of continuous data. The exchange can be anything. Next, we have histogram for test scores of a class. The test scores themselves, they are discrete. Number of students, also discrete. Stem and leaf diagram for the height, again, height, measurement, that would be continuous. So you have some homework questions found on this page. Please complete them and submit them to your teacher.